Most people buying an electric vehicle are thinking about two things: how far can it go, and how fast can it charge. Both of those come down to the battery. And right now, researchers are rethinking how battery electrodes are made at a pretty fundamental level. Let's back up a little. Inside an EV battery, you've got electrodes. These are the layers that store and release the electrical charge. Making those electrodes, well, is everything. For years, the standard approach used a wet process. You'd mix up the active materials with a liquid solvent, coat them onto a surface, and then dry the whole thing out. It works, but it's slow, it uses a lot of energy, and the solvents involved aren't exactly friendly to the environment. Then came dry electrode technology. The idea is exactly what it sounds like. You skip the wet slurry. Instead, you process the electrode materials in a dry state. Tesla's been pushing this direction with their 4680 cells. It's faster to manufacture, uses less energy, and cuts out those solvents entirely. But here's where it gets complicated. The dry process that most people have been using still relies on a specific material to hold everything together. That material is called PTFE. You might know it better as Teflon. It's the same stuff that keeps eggs from sticking to your pan. In battery electrodes, it acts as a binder. You mix it with the graphite and other materials, and it forms a kind of fibrous network that holds the electrode together. PTFE does its job, but it comes with real downsides. It's a fluoropolymer, which means it contains fluorine-based chemistry. That raises concerns about manufacturing waste and disposal. There's also the issue of cost and supply chain. And from a performance standpoint, PTFE doesn't conduct electricity. It's just there to hold things together, which means it's essentially dead weight inside your electrode. So a research team in South Korea set out to solve this. The group from the Korea Institute of Materials Science, working with colleagues from the Korea Electrotechnology Research Institute, developed what they're calling a PTFE-free dry electrode process. And the key to making it work is something called shape-controlled graphite granules. Graphite is the main active material in the negative electrode of most lithium-ion batteries. That's where lithium ions are stored when the battery charges. The way graphite particles are shaped and packed together matters a lot. If the particles are irregular or poorly arranged, you get gaps and weak spots. That hurts both performance and how well the electrode holds together. What this team did was engineer the graphite particles themselves into controlled granule shapes before processing them. Think of it like the difference between dumping random gravel into a container versus using carefully shaped pieces that stack and fit together efficiently. The controlled shape allows the graphite to pack more densely and more uniformly. By doing that, they found they didn't need PTFE at all. The shaped granules can bind to each other well enough through the dry processing method without a fluoropolymer holding everything together. The electrode maintains its structural integrity without it. Now, why does that matter for the driver sitting in the car? A few reasons. First, you can pack more active graphite into the same electrode thickness. Less binder material means more of the electrode is actually doing electrochemical work. That translates to higher energy density, which means more range. Second, the electrode structure is more uniform. Lithium ions can move in and out more evenly across the electrode surface. That's what determines charging speed. When the pathways are clear and consistent, you can push more current through during a fast charge without damaging the electrode. That means faster charging without the degradation penalty you'd normally expect. Third, cutting out PTFE simplifies the supply chain and reduces the environmental footprint of manufacturing. Fluoropolymers aren't the easiest materials to handle or dispose of responsibly. This is still research stage work. There's a gap between a lab demonstration and a production-ready process that battery manufacturers can use at scale. Getting the granule shaping process to work consistently at high volume while keeping costs competitive is the next hurdle. But the underlying concept is solid. If you can get equivalent or better performance without the problematic binder, that's a genuine step forward. It's also worth seeing this in the broader context of where battery research is heading. The industry is under real pressure to improve energy density, cut charging times, and make manufacturing cleaner. Dry electrode processing is one of the more promising paths because it addresses all three at once. This work takes that path a step further by removing one of its remaining chemical dependencies. The fact that the electrode holds together without PTFE also opens some interesting doors for future development. If researchers can tune the shape and surface properties of those graphite granules even further, there may be room to optimize for specific use cases. Maybe a version tuned for maximum range, maybe another tuned for ultra-fast charging in commercial fleet vehicles. The granule shaping approach gives engineers a new variable to work with. For now, the big takeaway is this: making better EV batteries isn't just about finding new chemistries. Sometimes it's about rethinking how existing materials are processed and structured. Graphite has been in lithium-ion batteries for decades, but changing the shape of those particles at the manufacturing stage and removing a binder that was just getting in the way could meaningfully change what that battery is capable of. That's a reminder that some of the most impactful advances in tech aren't always completely new ingredients. Sometimes they're smarter ways of using what you already have.